So my name is Jose Martin Garcia. I'm the manager of the special projects team here at Wolfram. And today I'm happy to start a series of 6 short talks in which my colleagues and I will talk about Tabular, a new and very powerful data container in Wolfram Language. Feel free to post questions at any time talk in the chat window. And my colleagues will address them as they appear there, or at the end of the sessions today, we will have the order of 10 minutes in which we will address questions there too. So let me start with discussing what tabular data is. So tabular data is everywhere. Tabular data is defined by organization in rows and columns. We can find it in spreadsheets, in databases, in general tables of data, and this is the general organization. You can understand that in rows we have measurements or observations or objects, and then in the columns we have variables or properties about those objects or observations. Typically, we will have just a few or a moderate number of columns, but the number of rows can be huge. So these large amounts of data can be handled efficiently by making use of homogeneity of types in the columns. So typically, we will have all the elements in one column being categorical data or numbers or dates or some other things. And some of the elements can be missing. So Wolfram Language 14.2, released just a few weeks ago, introduces a new data container which specializes in this type of data, and it's appropriately called tabular. There are many ways in which you can construct a tabular object, and you will see them during these talks, but probably the simplest one is simply providing a matrix of rows and columns in the first argument of tabular, and then in the second argument, you give the names of the columns. And so we evaluate this, and there you have your first tabular. So notice that we have some indications of types. So this is an indication of being a column of strings, and then we have a tooltip. So for example, this is a column of integers in 64 bits, or this is a column of dates with date granularity. So the standard workflow with tabular is represented here. So Wolfram Language 14.2 already adds more than 30 new functions to work with tabular, and the traditional structural functions of the language have been updated to work with tabular too. Tabular already offers nice visuals, and in future versions of the language, we will improve on that. There is extensive documentation already, and we can we have a tabular guide with let me see how I can show you this. Right, so this is a tabular guide for tabular in which we have various sections and the functionality about tabular. And we have also added examples of data in the Wolfram data repository. And here, let me share with you this again. So here you have various data sets that will be used during this talk, these talks. Okay, so as I was saying, this is the general workflow. The key idea is to go through several steps, communicating always using tabulars. These are the tabular objects. And so we will start with getting data sources, cleaning them, then understanding what you have by a process of transforming the data, visualizing, modeling, and then you can communicate the results. So based on these workflows, we have separated various talks today. And my talk is the introductory talk. And then Rob Knapp will talk about tabular transformations, Gosia about data cleaning, Sean Sheren about data sources, Brett about data visualization, and Julio at the end about data modeling. So it's a slightly different order, but we thought this order will help you understanding better how various functions are introduced and how they work. So let's describe here some tabular basics. So again, let's construct a tabular. Now it's going to be a little bit bigger. So here I have data about the G10 countries, which are actually 11. And we have this matrix of 11 rows and 6 columns. And we have the column keys, which are these 6 column keys. So this is the tabular we have, right? And you see again how we have different types. This is a column of entities. This is a column of expressions, which are these images. This is a column of strings, a column of quantities, with magnitudes being reals and the units being square miles. So this is population, and these are dates, the date of independence of each of these countries. So once you have one of these tabular objects, you can extract individual entries, as usual in the Wolfram language, using the part language. For example, this is the area column of the first row. So we are referring to the area of Belgium. So here we have the area of the last row, which is the United States. We can extract a whole row, and to do that, we return the data as a new object called a tabular row, which can be normalized into an association with the various keys used for the column headers and the entries of the corresponding row. We can also extract a column, and we return the result as a tabular column. A tabular column is the object that contains a type. So this is the type. It has 11 elements, and this is telling us that none of the elements of the column is missing. We can also normalize it, and we get a list of quantities. We can also normalize the whole tabular, and we get a list of rows, meaning a list of associations. Okay, so this is about extraction. Now, some of the basic properties of the tabular object are its keys, the keys that we introduced here. That's a list of strings in this case, or the types. If we call column types, we get an association of the type associated to each of the columns. So again, entities of country domain, expressions, strings, quantities, etc. Okay, let's continue with basics. So let's take again our G11 tabular object. So now, how do we add a new column? For example, we are going to add a new column called density, computed from 2 other columns, population and area, right? So we just divide the population by area. So we do this, and we see that we have added a new column here. It's a quantity column, of course, with proper units, peoples per square mile. And it was added at the end by default. Here, we will use the same function, transform columns, to do several things. First, we specify that we want the new density column after the capital column. We use this, some sort of anchor column, to place the other one. Then we say, okay, the population is going to be changed. Notice that this is a new column, but this existed already. So this is going to change the population column. We are just going to numerize it. We are going to apply n. So we are going to change from integers to reals. And finally, we are going to remove the independence column. So you see here, we evaluated this. We got the new column placed where we asked for. Population changed from being integers to being reals, and the independence columns has disappeared. So Rob will talk a lot more about transform columns and other functions, and Gosia will also discuss other operations that you can perform on tabular objects. I wanted to mention here that tabular specializes in the 2D rectangular case. We always had in Wolfram language, or for many years, another data container called dataset, which specializes on more general hierarchical, possibly rugged data. And dataset treats all levels in the same way, while tabular, you have seen that it treats rows and columns in a different way, right? It requires homogeneity of type in columns. So for example, take again our 3 rows of our tabular object. We can convert it into a data set, and we can convert it back, right? And so this shows that for the common case, the rectangular two-dimensional case, they can work both together and they can convert into each other. Okay, let's look more about types. For example, let's look about numeric types. Sorry. So here we have a tabular with a column of integers, a column of reals, and a column of numeric expressions. Notice that we also have a missing object here. And if we ask for types, we see that the presence of a missing object didn't spoil the automatic choice of types. So this column is still recognized as a column of reals. We can now say, I want to convert my column of integers in 64 bits to column of integers in 34 bits, right? And so there is this function in general to change the types of a column. Let's do also examples with dates. For example, let's take 100,000 random dates in this year. If we take the date 50,000, we get that one, which was randomly generated. We can insert all those dates into a tabular column. And of course, if we extract the date number 50,000, we get the same one, right? Again, same language of part in Wolfram language. Now, tabular column is a lot more efficient in representation, and tabular takes advantage of that. For example, you see our dates were originally a list of 36 megabytes, while tabular column stores the same dates in less than 1 megabyte. Computations are also faster. For example, if we compute the mean dates, we get that one. If we do the same computation with tabular columns, it's a lot faster, many orders of magnitude faster. For example, we can now insert 30,000 missing entries at random positions into that list. We put that new list in tabular column. You see, because there were many repetitions in this random integer list of positions, we get this number of missing entries. And now we can still do the computations, and mean will not get confused by the presence of missings. It will just ignore them and do the mean on the non-missing values. Tabular is very, and tabular column is very efficient in the dealing with types, and it can handle all the numeric types of the Wolfram compiler, which are all of these, and then several other types of the compiler, plus other ones that have been added specifically for tabulars, like dates or entities, etc. So there are many types that it can take advantage, and in the future, we will add more. Finally, I will end up with the last slide showing an example of working with a large tabular. Here, I have a file of 600 megabytes downloaded from NASA. It's a file about asteroids. And import takes about 2 seconds in downloading it. You see that the file is represented even with a smaller size. This file has 720,000 rows with 80 properties. And this is the tabular that we get. Notice that the original was a CSV file, all with strings, and the import of this object already assigned proper types to all these columns: strings, numbers, reals, integers, even dates. A nice way of getting an idea of the structure of some very large tabular object is using the function tabular structure. For example, here we will have in this column, we will have the column keys, and here we'll have some of the properties that we may be interested in, like the type, like how many elements are not missing, how many are missing. Some columns are completely missing, and then we associate to them type null. And here we have the byte count. We can restrict, for example, to the columns that start with letter E. So we get these. Or we can ask for specific properties, which are documented in the ref page. For example, there is one called count distinct that will tell you how many values of these 720,000 are actually distinct. In this case, for example, eccentricity of the asteroids are all different, but the epoch dates used for representation of orbital elements, you see there are only a few values. We can take advantage of that by categorizing, which means just store the different values and use an index as value for those columns. And then this shows that by just categorizing one of the columns, the column epoch, this one with 3 elements, we have gained 5 megabytes. So you see how by categorizing other columns, we could gain a lot of space, a lot of memory. Okay, so this was a quick example and a way to show that we can handle really large tabular objects. And here is what I finished. I will let now Rob Knapp to continue talking about tabular transformations. Thank you so much.
Okay, I'm going to be focusing on the transformations, and the transformations are actually quite important because they're fundamental to a lot of the operations you're going to do, because essentially all the operations each transformations in some sense. Now, since my time is limited, I could talk for hours on this, but I'm just going to take a super simple data set, which comes from the resource data about survivors of the Titanic shipwreck. And it's a small data set. It's got like 1,300 records. Okay, so before I actually do any transformations, I want to emphasize what the data model is. Jose sort of talked about this a little bit, and that is the idea of the normal model for what it is. So let's do normal of Titanic, and let's take the first 3 rows of that. And that's a list of associations, okay? And so basically, the column names are the keys and the associations. You notice they're all the same, they're uniform. And the rows are the individual associations themselves. So for example, using this model, you think, okay, what am I going to do on this list of associations? Well, part would take, the first element would take the particular association out, and the second element would choose the key. So if I do, Titanic, the first 3 parts of that, I get the first 3 rows of the Titanic, because that would be the first 3 elements. And the normal of that, of course, is exactly like the normal I had above. And so when you think of the basic transformations, think of this model. Think of working on a list of associations. And I think if you have that model, it will be a lot easier to understand how the transformations work. Okay, so before I get one more thing to talk about is the actual storage format. So for making efficient transformations, it helps to understand how the data is stored. So tabular is stored in memory using a columnar format, as Jose showed. And each column has an element type, and that's both for memory and operational efficiency. And the column memory can be shared between different tabular column objects. So a tabular object itself is immutable, and a tabular column itself is immutable. But a tabular column can be shared between, amongst any number of tabulars. So it's a little bit like a Mathematica, a Wolfram Language expression, but it's a vector valued expression instead of a scalar expression, which is what you're used to using. Okay, and then there's another command called from tabular that converts from tabular to various forms. And one of the forms that's particularly useful is columns. And if I look at from tabular of columns, I get an association of columns, okay? And this actually is very close to what the actual internal representation for tabular is. It's a bunch of keys, which is class, age, sex, and survive, and then these tabular column objects. And so there are going to be some transformations. And so if I can work on things that work with a column at a time, then I'm going to have things much more effective. Then there's some of the transformations actually work with this column-wise organization of data, as you'll see. Okay, so let's talk about what transformation commands there are. There are a lot. There's things like part, which selects parts, key drop, key take, those select things. Pick has been enhanced to work with Boolean tabular columns, so true and false values in tabular. There's sort and sort by, and delete duplicates by. And then there are new functions that are designed to work with tabular. And I'm going to focus in this talk on transform columns and aggregate rows, but there's a whole bunch of others. And almost all of these below are essentially based on transform columns. And in fact, any of the by functions are based on transform columns or construct columns. So understanding these two functions will get you a long ways in understanding when you look at a new command you want to work with tabular, understanding how that might work as well. Okay, so the first one is transform columns. So basically we have a tabular, we give a new column name and a function, and that creates a new column with name call by transforming the tabular data. So remember, in the data model, each row is an association. So within function, you can use pound survive to refer to the element of the association which has key survived, okay? And so when I run this transformation, I'm going to get a new column named S01 here, okay? And instead of having trues and falses, it has 0 and 1s. And you'll see in a moment why I wanted to do something like that. Another example is, let's just make this a little more compact. I'll call it Titanic 1, and I'll just make the sexes F and M instead of female and male, just to make it more readable. So that's an example of changing something in place. I changed this in place as well. So often you want to do chains of things in place because that gets you where you're going. And when Gauche shows the cleaning stuff, you just typically want to replace your table with one with columns replaced in place. Okay, so now there's one more that shows you the basic transformation, but there's also other types of transformations you want to do. And there's a thing we came up with column-wise value, and the description here is quite complicated. It does a lexical replacement of column, and I'm going to actually work through what that actually means. And what it allows you to do is it allows you to use column-wise things that have to be computed on a column-wise value in a row-based transformation. Because remember that transform columns maps over the rows. So we want to make sort of an exception to that rule is what this. And there's also a column-wise thread if you need to have the results threaded over all the rows. And I don't have any examples of that, but I think if you understand column-wise value, it would be fairly easy to understand. So here's a function. I'm going to call this, and sometimes it's convenient to define functions that I can repeatedly use, and I'll use this again a bit later in the talk. But basically, I want to have I want to classify ages, whether they're older or younger than the median age. Okay. But to do the median age, I need the entire age column to do that. So I wrap column-wise value around that, okay? And then this value gets put in, and then it computes the age is less than or equal to that. So let's do that. And then I can do the transform columns of this, okay? And now I get a class of each person, whether they're considered old or not. And in my world, it's great. People 29 are considered old. I mean, don't trust anybody over 30, right? So we're close to that. And that's an example of creating a new column, which actually, and this actually categorizes age in a sense. So it's a very simple transformation. So let's see how that actually works. So what I do first is I take, I'm going to show you. So remember that this is sort of a So I do this column-wise value, and so here's the median of the age column. So here I'm using from Tabular Titanic columns, okay? Remember, that's that representation. I show you that column-wise representation. Okay, and then I take the median of the age key, which is that tabular column, and a lot of functions have been overloaded so that they just work with tabular columns, such as median, mean, things like that. And that gives me the median age overall. Okay, and then I create a new function by replacing every instance of column-wise value with that value, okay? So now my new function, and this is the function that works row-wise, okay? And I get exactly the same results as before. So that's a quick example of how that's actually put together. Now, the internal code handles any number of column-wise values and so on and stuff, but it's really not much more complicated than that. Okay, so now let's look at the next function, okay, that I'm going to talk about. This is the aggregate rows. Okay, and this aggregate rows, the key thing to keep in mind is that it's going to work column-wise, okay? And the key thing about the idea is you have a group specification, you divide into groups, and you apply this function to each of the groups to get an aggregation over that group, and then you combine to get the results. And often the result is called, the method is called split, apply, combine. So we split into groups by distinct values of the grouping columns. Okay, then we apply the aggregation F for each group, and that's done column-wise. So when you think of aggregation, aggregate rows, you need to think of that column-wise representation versus the list of association representations. And that's why I spent so much time at the beginning talking about those representations. And you combine, each row makes group. So let's do an example here. Okay, let's compare the survival rate by gender. Okay, females survive way more often than males in the Titanic. That's interesting. Now let's do another one, and you can use a transformation rule to set up a group. So here I'm using that old age function. So I want to see, how did people survive based on whether they were older or younger? Okay, so that works very quickly. And what's interesting is there's an interesting weird thing here. Okay, so the survival rate amongst people who are older was 39% versus 42%. But what is this? Well, some of the ages were missing in the data. And so this is the survival rate of the people who didn't have an age classified. So when there's a missing thing, it'll translate through to that. And the operation of the old age actually propagates the missing. And there's really not time to go into that. Jose sort of showed that very briefly. Okay, so now let's consider, so here I've done one group. Let's consider two groups at once, sex and class, okay? So what it does is it takes distinct values of the list, sex and class, okay? And it shows this there, and it shows the survival rate. So the best survival rate are first class females, and the worst are third class male, or second class males, actually. Okay, and notice that these columns are emphasized in gray. They're what are called key columns. And to make key columns, it has to be unique identifier of a particular row. So in this tabular, if I say female and second, there's only one possible row that has that. So that's a way to have row keys as well. So now let's go one more step, and I'll show you how this command actually was done. The split, apply, combine. So first we split by group, and there's a group by for tabular, which divides the tabular into groups based on those groups. So here, female first, I get a whole tabular. Now the internal stuff doesn't actually create the tabulars because that's a bit more expensive than necessary, but the idea is the same. Okay, so I have a tabular for each group, and then on each of those tabulars, okay, so I make a table over those tabulars. I do the from tabular of this with columns. Okay, Mina survived, and that gives me my apply. Okay, so for each of those tabulars and the values there, I do the from tabular. That gives me the column-wise representation. I compute the mean, okay, and that gives me the means of the survived. And then finally, what I do is I combine them into columns, and here I'm adding the keys to make the whole tabular. Now this hasn't marked the key columns, but everything else in this table is exactly as it was above. So the last thing about aggregations is sometimes a really useful way to do an aggregation is to change the result of multiple, particularly when there's multiple groups. It's sometimes convenient to have a table. So this is actually the same results as above, but I've switched it so that gender goes down and the shipping class goes across. Okay, so it's very easy. It's much easier to make a comparison than it was in that previous tabular. And a super convenient feature of this that you can't do with just aggregate rows itself is this include group aggregates option. And what it does is it gives you aggregates for all the classes. So in this case, the all means this is survival in first class across all genders. This is the survival of all females for any class. And this is the survival of everybody overall in the Titanic shipwreck. Okay, so that's all I have to show. So now we can switch over to Gosia, who's going to be talking about using transformations and other things to do cleaning of data.
Okay, so hello, my name is Gosia Konwerska. I work as a developer for probability and statistics here at Wolfram. I'll be talking about tabular data cleaning, and turn on the video and we'll focus on the data. So first is what it's actually clean data, and I think that there's so many definitions as many people one would ask. What I think can be understood by tabular data cleaning is some modification of the data that will serve to better understand the data, and then this will lead to creating meaningful visualizations and some deeper analysis of the data. So my goal here is to present somewhat simple examples of transformations of tabular data. So some examples of data cleaning that may be selecting rows, columns, so the how to access the data that we are interested at, how to sort, how to then replace the values, and then how to deal with columns structurally in a way. So let's start here. How to remove a column. So, and when can this be useful? So this is an example of the data of Palmer penguins, so some measurements for the species. As you can see here, there is a column which is an index. And in the tabular, we have already rows that are being indexed. So that seems like this column is not really necessary. It can be removed. And the command for that, the function is delete columns. And we provide just the name of the data and the name of the column that we would like to delete. And then you see that the resulting tabular doesn't have that column. And of course, one can remove multiple columns at the same time, just provide the list of the names for the columns to be deleted. Okay. How to select column and rows. So that was a bit mentioned in the previous talks, and here I'll show you on a different data. This is the sales data that has some number of columns and some number of rows. Can kind of see column names, so column keys can be extracted using the column keys function, and we get the list of all the names for the columns. And if now we want to select the specific columns from the data, I can use the somewhat simplified part notation, which first asks us to put all the rows that we would like to see. So if we are selecting columns, we can put all, so it means we want to see all the rows for the selected list of columns. So that narrows the whole tabular into a smaller tabular with selected columns. If we ask for the single column, then the result is a tabular column that can be then normalized and listed. But sometimes you would like to have a tabular with just a single column. So that would mean putting here a list with just single name, and that creates a tabular with just a single column. Now, selecting a single row gives an object which is called tabular row. And what is important about tabular row, that it keeps the information about the names and the types of the columns from the original tabular. And that can be seen by comparing tabular schemas for these two objects. And this is the what the tabular schema contains. And the most, I think, important for us here, it's the types, column types and column keys. Now, there's another way that we could look at the selection of rows, and this is based on the values in a specific column or in a multiple columns. So, for example, we'd like to select all the rows from the original data for which the revenue, so values in this column, are above the median of this column, right? So here we have a select function, and we can then input a selection criteria here that will be a function of the column that we are wanting to narrow the data on. Another way is to use discard. Discard is a new function, and so that will do kind of an opposite action to select. We would like to discard, for example, all the rows that have region being Midwest. So this is the function region is Midwest, and now tabular in here doesn't have rows from the Midwest. Okay, so that was we were able in a previous example we were able to access rows by index and in columns by names, and there is also a way to access rows by values, in a way by creating names for the rows, and this is what we understand as a setting key columns. So let's look at this data here. This is a health expenditure through the years for some selected countries. And so when you look at this tabular here, here we have data for Australia through the years, right? And so it keeps going through the years. Then eventually it switches to Canada and it goes through the years. So if, for example, we would like to know what was the data for Canada in the year 2000, either I would need to keep scrolling, right, to find which row it is, which is not such a good idea, I think, because takes time. Or the other option is to use select with two conditions on the column of the country or column on the year. But we can also assign names to rows, and this means specifying which column or which columns will provide the names for the rows. And the only requirement for that is that the values of such key column or the pairs of values from multiple key columns are unique. So in this example here, we see that the values in the country column are not unique on its own, and the same, the values in the year column are not unique on its own, but the combinations, the pairs, are unique. So the pair can be used as a key columns. So we recreate a tabular, but now specifying the key columns to take country and year. And you see that in this resulting tabular, there is no row index, and this two columns, country and year, are shaded in gray, and they serve as a key columns. And then we can use the wrapper row key that will take the pair for the specification of the row, and we can extract the information for this row. So that would return us that will return the tabular row, and normalizing this will give us the association with the data we are interested in. Okay, let's look at another example of the data. This is some information about fatal collisions in all US states. And as you can see here, we already have a key column, which is the state abbreviation here. And when we scroll through this, we can see that this data is the rows are all ordered alphabetically by the state name. For analysis, maybe another order of rows would be more of interest, put it that way. So we can sort the data by a given column. So this would give us the states with the highest insurance premium first. So the reverse sort by, and then by will be referring to the name of the column for which we're interested. So we have the insurance premium first and New Jersey as a first row, or we can extract some subset of the data with, for example, the smallest values. So here, this is taking the 5 rows, so the 5 states with the smallest insurance losses. And the other functions that are in the same family working on tabular, that's sort by, and then corresponding take largest by, minimal by, and maximal by. Okay. Sometimes the data comes with missing values, it's incomplete. So here we have an example of temperature and pressure, some weather data with the missing. And tabular structure can tell you how many missing elements are in each column. So 2, 7 in temperature and pressure. And when plotting such a data, in this case, the temperature versus time, this plot will have holes. Temperature is a continuous observation, and one of the natural methods for filling in missing values is linear interpolation. And the function to kind of fill the missing values, or we call transform missing, on the data, with the method here given as a string as an interpolation. By default, the linear interpolation is being used. And now when plotting this, we'll see that we have a continuous nice plot without holes. And there are other methods available here for the transform missing, and they also can be specified on a column by column basis. So here this is temperature goes to mean means fill the missing in temperature column with the mean of the non-missing values, and in the pressure column take the nearest element that it's not missing. And then you can see here again the plot of temperature in time that we have the mean filling the missing in the data. Okay, so that was replacing the missing, and generally we can also replace all the values in a column. And why would we do this? For example, in this case, this is a cardiac disease data, so some medical patient data of patients. You can see here age or resting BP, cholesterol levels, but also there is a column here that's called chest pain and just has numbers. Okay, and I am not coming from a medical profession. I don't know what these numbers refer to. Maybe it's the scale of pain. When we look at the column descriptions of this data, we see that the chest pain actually is a pain type. So the coding here refers to the type of the pain. And for me, if I would like to do more analysis on that, it would be easier to actually see the descriptive values in the data. So that could be done by specifying the replacement rules and then using transform columns when the chest pain column will be just have replacement using the rules that we specify here. So the new data will have chest pain being now a string and being descriptive. And this will then look clearly when we aggregate rows, for example, to compute the mean cholesterol, when grouping according to the chest pain. So each group now will give us a descriptive value here. And of note is that, of course, doing a replacement of the values in a column will change or maybe not, depending what happens. But in this case, what happened is that the type changed. So the column type of the chest pain originally was integer type, and through the replacement, the type now changed to string. And generally speaking, the changing of the column type might be something that is needed also to better describe the data or analyze the data. Because what happens is, for example, often dates come as strings. So in this case here, the date column is a string column. And we can see this when we extract the column types of the data. And we have a new function cast columns that will change the type of the column into a given type. And this is maybe a funny example because we're changing a date column into a date type. So its date goes to date, but because depending on which side of the arrow this date is, has a different meaning. So right now, this date column has a different type, which is a date type, which has also information about the granularity, calendar, and time zone, etc. The integer numbers can easily be cast into reals. So the sales can be changed into the reals. And you can see that the city data can be grouped into the categories, and instead of just being strings. So if we ask city to be categorical type, then we see that we have here a categorical type with the types being listed here as all the cities from the original data. Okay. rename columns. So we change the types. We will maybe want to change the column keys, and that might be very simple scenario. We have a function which is called rename columns. But what I have here, I would like to show maybe an application of changing the name by of the columns by adding a level to a column key. So this data here is given in a monthly observations for a year. So we have a key column that it's a year. And what we could do is to group the months into quarters. And so what we gonna have months and then quarters as a list here, and create the new keys that will be extended key, and the top level is which quarter and then which month. So you can see that now renaming the months, so all the keys that were the months into the new keys will create a new structure on the keys. And so in a way visually it's maybe easier to parse, to group columns by some kind of a property. In this case, it's the time. And also what we can do here is we can refer to the keys by just providing the top level and then having anything else follow. So computing the mean for all quarters for each year, this function here will extract the column keys that match this criteria, so that the top level will be a given quarter, and then construct columns will create the new tabular from the original, taking the year column and then creating the new columns with the mean from the existing columns here. Okay, splitting columns. So sometimes the data, like here in the car models data, we in this column name have information about the car maker and also car models. And it might be nice to split this into the two columns. So the transform columns, we can create the two columns kind of on the fly by splitting the single one. We'll be padding with missing if there's no model specified. And here we're gonna place this before the origin, and also when we send the name column to nothing, that means that we're gonna delete this column from the data. So now we have two new columns, maker and model. It's easy to then count how many car makers were included in the data. This is using aggregate rows. We create the new column total, and then we'll reverse sort this by this new column. And then it's easy to say visualize all these car makers that have at least 10 models included in the data. So there will be pie chart on the selection of the above tabular. And the last example here is combination. So combining two columns, maybe more. The data here, it's New York City tree census data. So that's from 2015. Yes, many folks went out and did a census on the trees on the streets of New York. And this is, over 680,000 trees. When we look at this data, it has also many columns. But we see that one of those is the latitude and longitude, so for the tree. And this latitude and longitude can be combined into a single value of geoposition. And this is again using transform columns, placing this new column after the longitude. When you look at the column keys here, we have our geolocations here. And now we can visualize, for example, locations of the dead trees using geographics on the selection of the data that contains only the trees with the status dead. So this is the last example, and I thank you, and I will now let Sean Charon to take over with talking about tabular data sources.
Hi there, I'm Sean Sharon. I'm a manager of software engineering here at Wolfram Research, and I am really excited to be talking about bringing data into Tabular. Now that we've gone over what Tabular is and what you can do with it, well, how do you get your data? Let's dive right in. Okay, so hopefully everybody can see my screen. And we'll go back to the beginning. This part is about tabular data sources. And we will go over some significant updates in traditional ways that you've gotten data into Wolfram Language, such as import of some various formats like CSV and TSV, but also the introduction of these new structured formats that are very efficient for dealing with much larger data than something like CSV or TSV, which are text-based. We also have some updates in spreadsheet and statistical formats and some new functionality that will allow you to more simply connect to your data no matter where it is. So first, we'll talk about the significant updates in CSV and TSV, mainly performance improvements. Well, like Steven said in his blog post about 14.2, it's time to bring us your gigabytes. Historically, we've had flexible and powerful functionality that seems to just work, and this is no exception. Bringing huge tabular data into the language is just as simple and flexible to code as you would expect Wolfram Language to be, but it happily brings in your huge data sets no matter where they live. So in this CSV example, where we have 2 gigabytes of data and many, many rows and columns, the performance increase is nearly 30 times faster from the data element to bring the data into Tabular now. So importing as Tabular enables performance that was previously unreachable. And now workflows that used to take minutes are down to seconds. We're also not just improving the speed of the functionality, but the kind of automagical behavior that you've come to expect from Wolfram Research. Headers will be automatically recognized, including even information about their types. And this is the type of thing that will continuously improve over time, even though it's quite robust already. And we can do something like just grab a very large CSV file, and why don't I just give it a try? Wow, it's already done. That was, well, for the first 3 rows, quite fast. Wow, how long is it going to take for this very large file? Wow, also quite fast. And we're able to very quickly scroll through all of these rows. Oh, this is the city of Champaign, but as you can see, no matter how many rows are here, it's very responsive with large data now. And you can also explicitly give data that doesn't have an obvious header. Like here's just a matrix where there wasn't a data or header included in your data. And say that we wanted the first line to be considered the header, you can just explicitly specify that with header lines goes to 1. And this is now your key column for the tabular object. And like I've mentioned, there's also type inference. So despite the fact that CSV is entirely plain text, when we bring this into a tabular object, you'll notice that age is already interpreted as integer 64, and survived is already a Boolean. And like mentioned in some of the Q&A questions, it's very easy, and with many of the methods that Gosha just went over, to convert these data types or specify the ones that you want given a tabular schema. So if we import this tabular and take a look at its types, we can see that we actually have properly imported integers and Booleans. And now, again, since tabular is a homogeneous type column object, every single column here, every item in the column, every element will be of the same type. And we also have improved missing detection. So if your data comes in with a variety of missing values that are represented as something like null or NA, these are typically automatically detected with no additional work. And you can even modify this behavior using missing value pattern. There's some backwards incompatible changes in import and export of CSV, but this is absolutely a feature. We mentioned before, dataset is it's a data model that is hierarchical and can be extremely flexible. But in order to achieve the performance, the raw performance that's needed for modern workflows, we are heavily focusing on CSV and TSV being absolutely cutting edge. And The workarounds to your existing workflows are very simple and documented in the possible issues section. We're also always here to help. The new formats that we introduced are really exciting. The performance is really incredible. Every time that I've had to interact with data in the wild that I've gotten in one of these formats, things really were quite simple. So if we look at these formats, the first note is that they're columnar by default. Tabular is the default element for these formats. They allow you to store columns of various types, and that those types could even include arbitrary Wolfram language expressions. And we support various compression methods. So here you'll see that this flag column is an inert expression indicated by this little blue bracket badge in the corner. And these are actually Wolfram language graphics. And string columns will be indicated by this little double quotes. The other columns will be kind of obvious in the fact that they're either numbers or have some sort of unit. Now, if we go down to arrow IPC, this is based on the arrow in-memory format, so no translation is necessary between the file representation and the in-memory representation. What this means is that we can use memory mapping to avoid deserialization, and we can also pass around tabular data internally to heavily optimize workflows. Typically, arrow IPC files don't use any compression, but that means that kind of in your in-process workflows, when you're referring to the data, it's at full speed. We're already taking advantage of using it in our operations under the hood and will continue to. And we also support files and data that are either efficient for streaming data or for accessing the file randomly. Different workflows will have different ways that you want to save your data or that your data comes, and we are strongly committed to supporting all of those workflows. Parquet. This is the format that I end up using the most. It's a maximal space efficiency. It's optimized for disk I/O, has very good compression ratios, and even though it may be slower to arrow IPC due to the compression and decoding needed, it's often really nice to work with the file sizes and still quite fast. ORC is very similar to Parquet, but supports fewer column types. And in a quick performance comparison here, we can see that compared to CSV, these formats are still significantly faster because they're able to be stored so efficiently. But even compared to previous versions, these types of timings for such large data, 2 gigabytes of data, would not have been achievable. So let's look at updates in spreadsheet and statistical formats. Similar to CSV and other formats, all these spreadsheet formats, in addition to these statistical formats, that might be relevant to your domain more in particular if you use a lot of SAS or SPSS. But basically everybody has some Excel data somewhere. We have this tabular element now, which will bring the data directly into a tabular from even an Excel file. There's a tabular association element, which, had I not asked for the first one, would give you an association of the tabular, the name of the sheet, and the image is the name of the sheet, which is also imported as a tabular. And when possible, it still has automatic header detection. The last thing that I wanted to go over briefly is data connection object. And what data connection object is a object, a symbolic representation to some remote resource such as Amazon S3, Amazon Blob Storage, Dropbox, etc. So you can create a notebook with your remote data sources kind of at the top of the notebook. It provides authentication or a dialogue so you can give your own credentials and then pass the notebook to somebody else, and your colleagues can work on the same data but use their own credentials. This has control over refreshing when you pull in the data or getting locally cached results. And our list of supported data sources is about to grow faster than ever. This is seamlessly integrated with import, and I think that the integration will continue to improve over time. So let's take a look at what it is. We have a data connection object. This is purely a reference to where the data might be located and hasn't done any form of authentication. As soon as you work with a data connection object, say to get its file format, because this is referring to a remote file, Parquet is the file format. We can just call import directly on it, and it's retrieving the resource remotely. Using a data connection object, what we're hoping is to provide a workflow that whether your data is on some SQL server or in some remote location, you can do an entire one-line analytics such as aggregating the expression types. For each expression here in this expression row, we can get the mean of this numbers column. And I don't think that there's a syntax out there that's as efficient or simple as this. And I'm really excited about it. With that, now that you know how to get your data in, let's talk about how you can visualize it with Brett Champion.
Hello. Relies on a common syntax across all the data visualization functions. And that is using a rule syntax with your tabular object on the left-hand side and the column name or column names that you want to visualize on the right-hand side. And so if you are familiar with the visualization functions, this should be hopefully very intuitive. So for something like list plot or list line plot, you can either specify a single column, in which case it's taken as the Y values, or you can specify a list of columns, a list of 2 columns, in which case you're specifying the X and Y coordinates for the plot. If you go up to something like list plot 3D or list contour plot, then you're specifying a list of 3 columns as the X, Y, and Z coordinates, similar to how you would specify XYZ triples for irregular data for those functions. In something like histogram or bar chart and pie chart, you're going to specify the column that represents the one value that contains the values that you're interested in displaying. And one of the nice things about using Tabular for visualization is that the visualization functions are able to see the type information in the tabular object and automatically make use of it. Whether it's a time column or a date column or even categorical ordered or unordered data, we can make use of that. So we'll go through a few examples relatively quickly, and we're going to start with a data set of sales data for a theoretical company, and we have market sectors of who they're selling to and what region is doing the selling and what product they're selling and when they sold it and who the customer was and how many they sold, what the revenue was, what the profit was, and what their cost was. And this data set is a little bit bigger than I wanted, so I'm just looking at things for sales for the second half of 2015. And so I just used select to trim it down to something a little bit more manageable in terms of the data. So the first thing I'm going to do is a little bit of cleaning in this case. And so what I'm going to do is I want to, back up a moment. So I want to look at what my sales is over time. And so to do that, I'm going to aggregate my sales and all the numeric things. I'm just going to add them up, and I'm going to aggregate by date. So any sale on July 31st of 2015 is all going to get summed up in terms of revenue, profit, cost, etc. And now we can create a plot. And so we have, this is sales 2 aggregated version. Sales 2 is my tabular, arrow, string profit. And so this is just pulling numbers from this profit column in order, starting at 984, then going to 4,000. And so if we look at this, there's 984, there's 1,000, somewhere over here is 4,000, etc. I guess there's 4,000, there's the 10,000. And so great. I've easily created a plot of my profits, for those 6 months. It's not cumulative profit; it's just per day. Cumulative would be another operation on this table. We can look at what goes into that profit. What was my revenue and what was my cost on each of those sales? And so here I'm giving 2 rows, and this is probably the most complicated of the things of this most complicated instance of the syntax, which is that I want to look at my revenue, I want to look at my cost, and I had to put an extra level of list around each of these, because if I just said revenue and cost, then that would put revenue on the x-axis and cost on the y-axis, and I want the series. And because I'm doing the series, so far list line plots hasn't known anything about where these came from, and so it's just starting at 1 and going up to about 120. But we have that date column in the table, and so I can include that. And so in this case, I'm saying my x-axis is date, my y-axis is my profit, and it sees the date column, it looks at the tabular, realizes that it is a date type, and automatically switches to a date axis as if I had either used date list plot here or done list line plot with a scaling function goes to date type specification. And as before, I can split out the cost and the revenue, and here we have a list of multiple things again, with the date and the revenue and the date and the cost, and then we get the 2 curves. As I mentioned before, if we looked at just a pair of things, and this is list plot instead of list line plot, because these points are not ordered at all, they're just going to show up wherever they show up. This is very random in terms of there's no our cost or revenue aren't increasing, and if you did this as list line plot, it would just be a big scribble of curves. But so we have cost on our x-axis, revenue on our y-axis, and you can see for this company that it's very tight band in terms of what they, how they're pricing their products. There's nothing that's really cheap to make but being sold for a lot, or not really anything being sold as a loss leader where they're losing money on every sale. Moving on to an example from statistical visualization, we're going to use the same initial sales data, and we're going to look at the quantity column. And so this is, how many items were sold at a time. And we can see that it's relatively evenly distributed. I mean, it doesn't skew toward large sales or especially towards small sales. It turns out that they're sort of selling everything in increments of 100 in this data set. And so that's sort of the finest granularity that this histogram can do. But we just said sales, quantity, and it started, it used that quantity column to generate the histogram. If we pivot the data by region and keep track of the quantity, then this effectively creates multiple data sets for us. And so I'm going to scroll over a little bit. And so the result of the pivot operation is that for quantity, we now have Northeast, South, Midwest, and West, where each region has their own sub-column, so to speak, their own column. And as long as the Northeast, South, Midwest, West are unique within this table as column names, we can refer them directly. If we had costs also split by Northeast, South, Midwest, and West, then we would have to use extended key to say that we want quantity Northeast, quantity South, quantity North, Midwest, and West. And so this allows us to create a histogram with multiple data sets. Because there's not a lot of big peaks in the data, this is kind of a jumbled mess. But if we stack the bars, then we get a better look. And so we have our pivots. We're going to look at our 4 regions. We're going to add a legend for the regions, and we're going to use a stacked layout. And we sort of see that the West region doesn't do a lot of sales compared to the others, and the Midwest and South do maybe some larger sales, and the Northeast does maybe more of the smaller sales, because these sort of the heights of these blue bars are below 500 are greater than the heights of the bars above 500. And then finally, we'll take a look at something involving bar chart. And so we'll do yet another aggregation and a little bit of a sort by, some more data processing before we do the visualization. And so we're going to aggregate our sales by region. We're going to sort by region after we've aggregated by region and product. And so, as Rob mentioned, this is going to give us a result with 2 key columns. And so within this region column, we have multiple rows that are in the Midwest. Within product, we have multiple rows that are Gizmo and Gadget and all the other products. But within this tabular, there is only one Midwest Gizmo row. There's only one Midwest Gadget row, etc. And so then there's a little bit of processing here to have something that looks nice in a format that I liked. And we can do a bar chart. And so we're going to take our modified tabular. We're going to extract the revenue column. We're going to use this formatted labels that I computed. Bar origin on the left, plot theme to make it nice and wide. And now we have our bar chart of revenue, and each bar corresponds to a region and a product. So the largest revenue came from gadgets sold in the South. And so that is a brief overview of how the visualization works. I think this syntax is something that people will adjust to very quickly. I think it feels relatively natural, and especially if you're already familiar with bar chart or list plot or slice density plot 3D or something, figuring out what items are going to go on the right hand side of that rule is not complicated. And so now we will hand over to Giulio to discuss modeling.
Hi, Brett. Thanks. Let me try and share here. Okay, so hopefully this is big enough. So, as I'm Giulio. Hi, I'm the lead of the machine learning team, and as such, as I was very interested in following very closely the development of Tabular, because our use case of these are broad and wide. So for 14.2, we started. It's kind of a boring thing for machine learning, but it set the stage for what's to come. So we did the homework of updating all our functions to support Tabular. And the syntax is something that if you've been using datasets with machine learning functions, is going to be very familiar. And incidentally, is also what this team is being using for Tabular. So the target column for machine learning operations is going to be extracted with the rule syntax. So you're going to have your arbitrary function here, your tabular object, and then the column you want to predict, classify, fit, or whatnot. So let's get into some details here. I chose this time the classic. Let's make this a bit bigger. The classic Fish Osiris dataset. This is a classic machine learning problem. It's a classification problem. You want to predict the species based on these 4 numerical quantities: sepal length, sepal width, petal length, petal width. So as you can see, these are columns with quantities inside. So this is a quantity real, centimeters for all of them, and this is just a string column. So again, if you did this data before, the syntax is exactly the same. If you've not, I think it's going to be easy to learn. You do classify tabular species. So this is what it's doing, is automatically dropping the species column from the tabular, of course, and using this as a target for the classification. We always had automatic feature type discovery in our automated ML functions. So this is inferring that these are like 4 numerical values here. If I had like different column types, it will automatically adjust. So for example, let's do something like a bit different, just for the sake of it live. Let's change classify into predict, and let's predict, which is doing regression, and let's predict I don't know, petal length on this tabular. So it's doing the running the optimization and the hyperparameter optimization. This is a small data set, so it's very fast. And now you see that we get the first column is a nominal column. Unfortunately, the tooltip is a bit small, but this is correctly, handling over the types of tabular. So there's not much you have to do here to update your workflow. Analysis function like classify measurements are working as well. Here I'm doing something just for the sake of expediency, no test train split, but just to show the syntax. You can put your tabular data inside classify measurement, and you get this summary. You can query in all the things like in this case confusion metrics for the classifier and stuff like that. So yeah, I mean, this is just updates. You can build new workflows staying directly into the Tabular framework. So you can create your custom pipelines. I'm gonna just show incremental changes of what you're seeing in the transformation talk. So here, for example, I take my C function, like a classifier function, and I'm using transform columns to add a new column. And here I'm using a feature of transform columns. If I just did this without this species thing here, the new column would end up at the end. And without, so without this, you get this at the end. With this is what is called, I think, I don't remember, like anchor keys probably, but it means an internal name. Basically, this allows me to specify the context. So I want like species first, and then put prediction in. So this allows me, like, this is a visual thing. This is indexed by name, so it doesn't really matter where it is, but it's nice to see them side by side if I want to compare them visually and see that they're mostly the same, luckily. Now, Rob showed column-wise value in his talk. I'm going to show here a nice use case for column-wise thread. So in general, all our machine learning functions are optimized for vectorized evaluation. Here, I'm using them in a scalar form. So I'm just running the cfunc one row at a time. And here you can see, if I run, instead of this thing, if I run like F1 or F2, one is a normal function and one is using column-wise thread. This is running the classifier on the whole column, and then it's distributing the result across the rows. So here you see that there's significant, I mean, a small memory improvement, but significant time improvement in not having to reinstantiate the classifier every row. We can build our own version of the confusion metrics using tabular functions. Here I'm adding to the prediction temporary matching column, which is just a true/false Boolean if the species and the prediction are the same. And once I have this, I can use aggregate rows and count correct, which is count true, and wrong, which is count false. I could use Boolean and do the total, but you get the gist here. More interesting, I can use a second argument third argument actually on aggregate rows. Here I'm using aggregate rows in operator form. This nice thing you can pipe, and I'm doing this so you can see the correct and wrong results by species, and you see this is essentially like a nice report for what happened class by class. So you see, I mean, these two are the closer classes, so they're more difficult to classify correctly, and this one is quite apart from the others, so you should get 100% classification result. Also, again, this is the training set, so it's kind of an easy problem. But I mean, this is it's very natural to insert your machine learning functions in these workflows. One note on piping: all these functions have operator forms, or almost all of them. So if you are the kind of developer who likes piping operators, you can do this, and then add this, and then add this in whichever direction you prefer, and you get the same result at the end if you prefer to read it this way. This is something that we support with all these operators, and you can also do it with select and other like older functions like select, for example, and then you're going to do something like species is setosa, for example. So yeah, this is, I mean, you can mix match new functions or functions, of course, everything is supported. Unsupervised machine learning has also been updated, showing like some of the less famous functions. For example, you can train a distribution on a tabular. So this is automatically on the full tabular with all the columns, training a multinormal distribution, extracting features from the rows. And once you have this distribution, you can do things like generate synthetic data, like random variate, one rows or multiple rows. Machine learning power visualization has been updated as well. Here we have like feature space plot, which is doing feature extraction and then dimensionality reduction, blocking this, reducing the dimension of these tabular rows to like 2, so I can actually plot them. I can do this in 3D as well, and just leave it at one more dimension to play with. As you can see, what I was saying before, like one class is very apart from the others. We see even like in an unsupervised way by just compressing the features, while the other two here are much closer. More updates are going to come in the next version. You can use the same syntax that we have here for classify. Where is it here? We'll train the classifier here. To train it, you can use it for our classic fit function, like linear model fit, non-linear model fit, and friends. But we are working on nicer way to bind columns and specify models that should come in the next version. Now, I think this is mostly all of it for our machine learning updates. We should probably move to the Q&A session at this point.
Yes, thank you very much for. I see that there have been many questions. Most of them have been addressed. Julio, there is a question probably for you about the choice of classifier algorithm.
Just saw it and left it for the end. Yes, the algorithm is automatically selected, and if you do provide a validation set, then you will use that. If you do not provide a validation set, the code uses cross validation. Is a k-fold cross validation on the training set. Is done in a smart way. So in this kind of whole like machine learning is AutoML. So there's kind of an automated pipeline to propose candidate algorithms with different hyperparameters, test them on a small portion of the data, and then we keep adding data we keep testing the methods and discarding the bad one and adding new data, and then you get the one last final training on the best method. So this is like in a sentence what these AutoML functions are doing. You have classify for data classification and predict for data regression, like scalar regression.
Thank
Tabular
you.
data for time series modeling. I don't remember any specific function that was, maybe some other people can pitch in here, but I mean, Tabular itself can hold the time series, but I don't think we have done anything specific for time series in this version yet.
That is correct. So you can convert between the the time series to tabular and tabular to time series, but in the time series models, the time series processes, the tabular is not yet directly supported.
Thank you, everyone, for all the great questions and answers that have been going back and forth here between our experts and the audience. That's a great collection, reviewing that in the Q&A. If you have, I see a couple more questions coming in. We can see Mitchell's asking about previous sessions, and Mitchell, you can send an email to us at wolfram-u@wolfram.com if you would like to specifically ask something about a previous session or handouts from the previous session, and we will try to find an answer for you. Jose or anyone else, was there anything else you wanted to share before we wrap up today?
No. Well, perhaps just mention that some of the questions have addressed things that we are working on, like joins or how to typeset money or with the different digits, a number of digits. So these are things that are being worked on right now, and yeah. So I'm sure the next version will have a much improved tabular.
Thank you.
And I think this applies also to the last question by Harald, the group by versus partition over. We are aware that we haven't implemented all the equivalent relational database equivalent functions yet, but I think for this version, the main focus was having a solid data structure, very fast, very optimized, and an initial set of functions to work with. This doesn't mean that this is at the end of the story. This is just the beginning of the story.
Thanks, Julio.